Good morning, everybody. I hope you can hear me well. And welcome back to the course on machine learning. I just wanted to, before we start, to give you a quick overview of the week. And you will also find the videos from the previous lecture on the GitHub, on the main GitHub site. You can find the video, the link to the video, and the link to the handwritten notes. So last week, we actually started to discuss neural networks and our deep learning methods. And we looked at the basic elements, and some of these basic elements were the feed-forward part, which we will repeat a little bit today, and also the backpropagation part. And we ended up last week by setting up the equations for the backpropagation algorithm. Now today, we are going to repeat some of these elements, and the scope is to actually build our own code for a neural network. Then, the week thereafter, we will summarize the calculations for neural networks, and we will apply these to the solution of differential equations. And most likely, next week, we will also start looking at convolutional neural networks. And finally, the last part is going to deal with recurrent neural networks and convolutional neural networks. So this will conclude the lecture part of the course. Now, I haven't set up anything for January, but most likely we will have some few sessions in January as well, where we can discuss the solution of the two projects. And to remind you of what we discussed when we met in person, the projects can be combined into one. Just to give an example, there's a group who wanted to look at the studies of models for spin systems like the Ising model or the Heisenberg model. So what you could do then is to use a regression problem in order to fit the coupling constants in these models. And then if you want to do a deep learning project on this, you could just simply repeat that part. And alternatively, you could actually run calculations with an Ising model and produce configurations and use these configurations to train and produce images of whether you are below or above the critical point in the Ising model. And then with these images, you could use convolutional neural network to see if you can classify whether this is a system which is below the critical temperature or above the critical temperature. So just to quickly remind you, for those of you who are familiar with the Ising model, the Ising model is a classical model for studying magnetic phase transition. So the system switches from being in a state with a finite magnetic moment, so we say the system is magnetized, has a finite magnetic moment, to a system which in solid state physics would be classified as a paramagnetic system, which is a system where the net magnetization is zero, and all the spins point randomly in all possible directions and sum to zero. So that is an example of a system which exhibits a phase transition at a given temperature. And using convolutional neural networks, you can train a model where you feed in images of the magnetic moment above and below the critical temperature. And then you can use these images to train a model which recognizes whether you're below or above the critical temperature when you feed in a new image. That's an example of how you could combine project 1 and project 2 with a classical linear regression and regression methods, or what we normally call the type of a pre-deep learning revolution methods with deep learning methods. So what I wanted to do today is, before we dive into the technicalities of building our own code, I wanted quickly to say, to remind you of where we were last week and where we ended. So let me bring up the whiteboard again. And unless you have any questions, I'm just going to try to repeat a little bit of the basic elements which we went through last week. By the way, feel free to unmute yourself and ask questions if you have questions, or just put them in the chat, and I will try to follow the chat as well. So we're going to switch to the whiteboard, and let's do that. So last week, we put up the basic elements of a neural network. So let's remind ourselves of the basic elements. And I'm going to use the shorthand NN for neural network. It's normally shortened to artificial neural networks, but I'm simply going to use an NN. And then I put an S here since these are neural networks. Now, what we need to do first is to define the model, or what we also call the architecture. So we'll use these as synonyma, and I'm just going to use them interchangeably. And in this case, we need to define the number of hidden layers. And as we discussed last week, the universal approximation theorem says that we can approximate a non-linear function with, to a given precision, with at least one hidden layer. So we need to specify the number of hidden layers and nodes in a hidden layer. And we can have many different hidden layers with different number of nodes, but in most cases, in actual cases, people would typically run with a given hidden layer, number of hidden layers, and a specified number of nodes, which is the same for all hidden layers. And then we need also to define what we last week discussed as the activation functions. And there are several ones of them which can be used. And you would typically run these as numerical experiments where you try different types of activation functions. And this defines the architecture of the model. And then when you've done that, you need to define the type of hyperparameters you want to deal with. And these are normally called renormalization terms or shrinkage terms. So these are normally called shrinkage terms. And typically you would have something like a parameter lambda, and this is multiplied with the weights, which we have in our model. And it can be the norm 1 or the norm 2. Norm 2 is pretty common, and these are the weight squared. This is a typical set of shrinkage terms which are normally used in the setup of neural networks. Then the next thing we need to set up is the way we want to train the network through the type of gradient descent algorithms. So I'm just going to put that in terms of these gradient descent algorithms, because there are many types of such algorithms. So GD algorithms. And when we set up these algorithms, I mean, we can use standard gradient descent, and that can be used in case you don't have too many parameters, but it's pretty common to use a stochastic gradient descent. Stochastic GD. And there is a whole family of these methods. So one thing you will typically add by default almost is what we call momentum. You can use different ways to update the learning rate. And the most common ones are given by this adaptive learning rate method with momentum. We have a root mean square propagation, RMS prop. There is ADAGRAD, adaptive gradient. And these are all methods which try to bring in information about the Hessian matrix in one way or the other one when we are updating the value of the learning rate for every iteration. Now, these are methods which we need to set up and have in the background when we are training the gradients. And then the final thing which we need to do is actually to define our cost function. And the cost function is the one which we use then to optimize the different parameters which we need. So this theta is now a common container for all the types of parameters which define the network. And last week, the way we defined this was in terms of the weights of the first hidden layer and the biases of the first hidden layers. So that would be a common denominator for theta 1, the first layer. And then we have for the second layer, and then the weight, the biases for the second layer. And this goes on till the final output layer. And we use the uppercase letter L for the final output layer. So these are the parameters which we want to train in order to find the best possible approximation, either in a classification case or a regression case. Now, let me just quickly remind you in a graphical way of portraying a network, the way we think of a neural network. So we would typically have an input layer. So we'd label that with an X. So this is normally called an input layer, and that can contain many different nodes. Think of this as an image. If you have an image with 100 times 100 pixels, that input layer would contain 100 times 100, which is 10,000 input nodes, and one input node for every pixel. And you see clearly that the dimensionality of the matrices, which are going to contain the parameters we want to find, can easily explode. And that is why later, when we are looking at images, we are going to look at a way to reduce the dimensionality of the problem through something which is called convolutional neural networks, where we use the mathematical process of convolution to filter down the dimensionality of an image so that only some relevant pixels are kept. Just to give you an example of that, if you're doing deep learning and image classification, you would typically, if you're looking at houses or bridges or whatever, you would normally never keep the full information about the color of the house, because we assume that to be pretty uniform, but you would keep information about where the windows are, where the doors are, where the corners are, etc. And then this feeds into the first hidden layer. So we have a 1 here. These are the weights, the unknown parameters. And this goes in to the first hidden layer, and it produces an input, Z1. So these are now vectors or matrices. There is a bias, which is normally set here in order to hinder that we by accident have weights which are very small, and that the training would accidentally stop. Now, this Z value feeds into, so this is the first hidden layer. So let's mark that with a red here. This feeds into the so-called activation function. And this activation function is something which we label as a Z, as a sigma. So this takes as input Z1, and that produces an output, which we call for A1. And that is fed into the next hidden layer. So we would have a Z2 here. There is a set of weights, W2. There is a bias, B2 here, and that produces an output, sigma Z2 here, which we label as an A2. So this is the second hidden layer. So let's just write that. That's layer 1. This is layer 2 here. And this continues all the way till the final output layer, where we have a Z of L, and that receives an input from A of L minus 1. There is a weight here, WL. This is with an uppercase L. This is meant to represent the final layer. So there's a Z of L here, and that produces an output A of L, so which we are going to label as a Y. So that is the output from the network. And this now is fed into the cost function. And this cost function is a function of this output Y. It's a function of the parameter theta, and it's also a function of the target values which we want to reproduce. So the target values are also fed into this function. So C of Y, of T, of theta, that is our cost or error or loss function. And this is the one which we want to optimize. So if you now look at this chain of operations, the way you can think of this, if we now just write it down, is that this final output, A of L of Y, is now given by this subsequent chain of mathematical operations, where we have a sigma of L minus 1, and this goes all the way down to sigma 1 of Z1. And this Z1 here is simply given by the weights of the first layer multiplied with the input plus the bias from the first layer. And then obviously this C1 of Z1 here gives now the output A1 from the first layer. So A1 can now be a vector or it can be a matrix. And we would continue this way with a feed-forward process and a back propagation process. So the final output, this A of L here, depends now on the input and all these parameters theta, where theta now is a collective container for all the unknown weights and biases for every hidden layer. And when we now are optimizing, what we will typically do then is to start calculating the derivatives. And last week, we actually defined these derivatives by using the chain rule. So the network, the basic algorithm, after we have set up, is first we need to define the network. So if we now go back to what we put up here, the basic elements, we need to define these quantities here before we start training the parameters. So first, so define the network. And this is the first page, which we repeated today. And then we would have a feed-forward pass through all L equal 1, 2, up to L layers. And every layer produces its own output. So this will produce outputs A1, A2, to AL, which is the final output. And that's the value which we want to compare with the target values. So we would also then initialize the weights and biases. And typically we would initialize them using, for instance, a normal distribution, and where we often let the values be pretty small in the beginning, but non-zero. And that hinders that some of the gradients will actually explode when we do the training. So the feed-forward pass goes through the whole network and produces a final output, which is the value which we have here. And that's the value which is then sent into the cost function. So we will have at the end the possibility to evaluate the cost function as a function of this A of L. And then we compare that with the target values T. And these are all functions of the parameters which we initialized. Then we have the next piece where we now want to train these different weights. And the way we train them is to perform the calculation or run through the calculation of the gradients. And this leads to the back propagation part. So the iterations which we are doing now will contain a feed-forward pass and a back propagation part. So that is one iteration. So back propagation. And what we are going to calculate then is the update of the gradients. So the updates of the weights, J, K of L, and the biases, where this L stands for just one specific layer. So these are the layers, L equal L. We go to L minus 1, L minus 2, and then we proceed all the way down to the first hidden layer. And then we have updated the weights and the biases. In order to do that, so this is one iteration. So one feed-forward part. Pass plus one back propagation part, prop part, is equal to one iteration. So if you think back to when you wrote a gradient descent algorithm, then you did this iteration something like 100 to 1,000 times. Now, in our case now, one iteration means one feed forward pass and one back propagation path. So when you've done the back propagation, then you have new values for the weights and the biases. And then you perform a new feed forward path. You get new outputs. You compare these new outputs with the target values. You recalculate the derivatives of the cost function at the output layer. So that means that when we start doing the calculations, what we want now is actually the calculation d theta at the output layer. And this is a quantity which we normally want to drive to zero. So the way we do this now is to repeatedly use the chain rule. And let's look at a specific example with a numerical or just a regression case where we take the mean value, the mean squared value, but without having the derivative, the number of data points. So we would have something like 1/2, and we have t minus, and then we have al, which depends on the input values, and theta, and this is a norm 2. So this is the mean squared value without the factor of 1 divided by n. And this is handy because this factor 1/2 gets disappears when we take the derivative with respect to a. Plus, we could have some lambda, some hyperparameters, which now will depend on the weights only. So this is a typical cost function which we would optimize in order to find the best possible parameters if we are dealing with a regression case. If you're dealing with a classification case, we would then typically have a cross entropy, which we discussed in connection with logistic regression. So if you look at the function here, there is actually not an explicit dependence on the unknown parameters theta. So this is the quantity we want. But if you now look at this, there is this function which we have here. There is no explicit dependence except for this omega dependence here. So we have no explicit dependence on the parameters theta in the first part of the cost function. So here we obviously have an explicit dependence on omega, one of the parameters. And in this specific case, we have to put in a theta L here, and we have a WL here. But if we look at the first equation, if we now leave out this shrinkage or hyperparameter term, what you see now is that we need to use the chain rule in order to get the derivatives. So if I look at this dc theta L here, what I need now, so suppose I want to calculate the derivatives with respect to the weights. So I would need WL, and I would need the derivatives with respect to the biases in the final layer. So these are the quantities we want to evaluate. Now, if I now take the derivative of the cost function, so suppose now that C of A of L of T of theta is now just given by 1/2, and then I have T minus AL, and this is just the norm 2 of T minus AL. And so we have an explicit function which depends on a function which depends explicitly on AL, but then we need, in order to find the derivatives with respect to dc of dWL, we need now to use the chain rule. So we end up with taking dc, dA of L, and then we would have dA of L, and then A depends on Z of L, and this is given by dC of L of dW of L. And we just remind ourselves that this Z of L is now given by WL, and it has an input value which comes from the previous layer of AL minus 1 plus this B of L. So this is the expression in a more compact matrix vector notation. So Z can be a matrix or it can be a vector. And then we remember also that A of L is actually given by this function L, the output layer, and then we have an A of L here. So if we're dealing with a regression problem, this activation function for the output layer is typically given by just the value which we are inputting itself. Sorry, this is not, the last one was not correct. It's actually Z of L here. And now you see that you can calculate these different derivatives. And what we did last time was simply to set up the backpropagation algorithm and starting with the final layer, the output layer. So what we defined then was a parameter when we now looked at the specific value at the end layer. This parameter here was now defined as sigma L, and then we had the derivative of that one, and this was multiplied with dc of dA of L. And you see now that this forms the first part of the equation which we have here. So we have now taken this term here, which is exactly the same as what you see here. And then we have this term here. So this delta L is nothing but what we have here. And if I take the derivative here with respect to WL, I'm left with this term here. So that means that my derivatives, which I need in order to set up the backpropagation algorithm using the chain rule. So if I take this equation here, what we have then, if we just put everything on the same page, is that dc of dWL is the same as this parameter delta L and multiplied with AL minus 1, where the AL minus 1 comes from this part here, because we are taking the derivative of Z with respect to W, and then we are left with the output from the previous layer. So this is the equation which we need to start with when we are calculating the derivatives. Then we can also show then that the derivative with respect to this parameter B, so dc d of B of L, is the same as this delta of L. I left that as a small exercise last week. And then we can propagate backward, where we now can find an expression for this delta J of L. So the backpropagation algorithm gives us this delta of little l. And now I'm just going to set this up for a specific node in a given layer L, where L now can go from L, L minus 1, L minus 2, all the way down to the first hidden layer. So this delta J of L, as we found last week, is now given by a sum over all the corresponding values in the layer ahead of it, L plus 1. So we're just propagating backward. And then this is multiplied by the weights in the layer L plus 1. And then it's multiplied by the derivative of the activation function with the input from that specific layer. So that means that when we are setting up a neural network code, we need to keep track, or we need to store the values for all the weights and the biases at each hidden layer. And then the basic gradient update is then given by Wj of k of a given layer L, which is then given by the previous value minus, and then we have a parameter eta, which then can depend on the type of iteration we're doing. So this is the learning rate, eta, and this is multiplied with delta J of L and multiplied with AK of L minus 1. So we need to store these values, which means that if we have a pretty deep network, you can easily see that if we have many nodes and many input nodes, then the network is going to be pretty large when it comes to matrix dimensionalities. And then we have Bj of L, which is then being updated by Bj minus eta times this delta J of L. So the basic equations which we need to have then are this equation here. We need also this specific equation here, and clearly the equation for delta. which is something we can define from the specific cost function which we have. And then we need this equation here. So the first three ones with the uppercase letter L are for the last output layer. And then we go backwards till we reach the first hidden layer. So we will go back and forth this way. So one iteration means that we just perform one update of this type here. So what you see here, these four equations which we have framed in, that means this one and that one, this one and that one, these are the equations of the backpropagation algorithm. The equations which you see here, these are the gradient updates as soon as we have the expressions for the different gradients. So this would just be the gradient for the weights, and this is the gradients for the biases. And then we simply have to set up these equations layer by layer. And we are going to see how we can do this now when we discuss the specific codes. So after we've run through the setup of the code, we are then going back to these equations here. And in particular, if we look at the derivatives which we put up. So if you look at this equation which you have here, this is just the first step in the backpropagation algorithm, where we calculate using the chain rule the derivative of the cost function at the output layer. And we have to set up this equation here, just to remind you of this, because the cost function which we define depends on the target values and the outputs. There's an explicit dependence there, and it's normal to not have an explicit dependence on the weights and the inputs to the last hidden layer. But we know then, by the way we have set up the model, is that the outputs are given as a function of z, and the z's are then given as a function of the input to the last output node, or the last hidden layer. Or rather, the last hidden layer is not hidden, it's just the output layer. Any questions so far? Hope everything sounds clear, so that you see the basic equations which we need to plug in. So what we are going to do now is to start with a simple example. And when we have gone through the setup of a neural network, we are going to go back and look at these derivatives in terms of the backpropagation algorithm and automatic differentiation. But what I wanted to do now is simply to go back to that simple case which we had with a so-called XOR gate or OR gate. And these were examples which we discussed last week. So what we had last week is an example which I'm going to set up here. So we can get started with that one first. So this is an OR gate or an XOR gate or an AND gate if we want to. So these are cases in electronics which are pretty popular. So what we will have then is two features. These are the input values, two features. So we have x1 and x2 here. And then if we look at the case of the OR gate, and the reason why I'm setting this up, it's because this is a very useful example to look at when we want to understand what is happening with a neural network. So what we have then is a table with inputs, x1, x2, and then we have the output, which are the target values. So in this case, I'm now looking at four types of inputs. So I have 0, 0, and that gives 0. If I'm looking at the OR gate, I have 0, 1, and that gives us 1. I have 1, 0, which also gives 1. And I have 1 and 1, which gives us 1. So that means that I could now define a design matrix. So my design matrix would then be given by just these values, 0, 0, 0, 1, 1, 0, 1, 1, and this now contains x1 and x2. However, if I wanted to, I could just feed in one set of values and then train a network. So just be a little bit careful now, because what I'm doing is to set up 4 input values. And that gives us 4 types of outputs. But each one of these is just one input, which now produces one output. So you could think of that as an image, and that image could have 100 pixels times 100 pixels and just one color channel, which means that you have 100 times 100, which will be 10,000 nodes. In this case, we have just 2 inputs. And then we could train just one image. So that's fully possible. And the output then of this network would simply be given by one of these values. But now we're actually going to train it on 4 input values. And this becomes a batch of input values. And this batch of input values gives us now a set of output values, which are those which we want to train. Now, what you could do now is obviously to duplicate this set. So you could just repeat it. So then you would have 8 input values. You could triplicate it, or you could have thousands of these. So suppose you have 1,000 duplication of this set, then you would have 4,000 entries. And that would be a batch of data. So this complicates a little bit the way of thinking, but I hope it's not too complicated. But at the beginning, you could just think of this as just one. Now, what we are doing now is to train a network where we want to train weights and biases, which should apply to all the input values. So if we now look at the network which we are going to set up, in this specific case, we are going to have a system where we have x1 and then x2. These are the input values. And then we could think of a hidden, just one hidden layer. So we would have 1 and 2 here. So this would be h1 and this would be h2. So node 1 feeds into this one, but it also feeds in here. So we would have a w11 and a w12 here. And then this x2 feeds in here. So we have a w21 and then we have a w22. And then we have in addition a bias, B2 here, and then we have a B1 here. Just a moment, I think I didn't want to put it like that. I want to have a B1 like this and a B2. So that means that Z1, since we have only one hidden layer, we don't need to put in the superscript indicating which layer it is. So we would have a W11 multiplied with X1, but then it receives an input from X2. So we have a 1, 2 times X2 plus a B1. And then we have a Z2 here, which is now given by W2 or 1, 2 times X1 plus a, this should actually be 2, 1 here, plus a W22 times X2 plus B2. And that produces an output, A1, which is simply given by sigma of C1. And we have another output, which is given by sigma of Z2 here. Now, these guys here, they feed into only one output. So that produces a Y, which is given by an output, A. And I don't put any subscript here. And that goes into the cost function, C, and that is compared with the target value. So these feed into this one. And there is a weight W1, a weight W2, and there is a bias, which I just called for B. So this Z here is then given by W1 times A1 plus A2 times W2 plus this parameter B. And then I know that my A is simply given by a new function as with Z as an argument. So let's look at the calculation of these different objects. So W1, W21, W12, and W22, these are the parameters which you now want to find. So this is an unknown, this is an unknown, this is unknown, unknown, same with that one, same with this. And finally, this is also unknown, unknown, and unknown. So we have in total, we have 9 parameters which we want to train. And then what we would have then, when we are setting up the matrices here, we see now that the weight matrix, W1 or W, for the hidden layer is given by W11, W12, and then I have a W21 and a W22. So we need to then perform these calculations, and the design matrix, so this is a matrix which has dimensionality 2 times 2. My design matrix is the one which I now want to multiply with it. I could just keep one of the input values, but now I'm just going to take a batch of values. So this is a matrix which has dimensionality 4 times 2. And then I have my vector B, which has only 2 values. So this is a vector of length 2 times 1. And that means that when I multiply X with W, this becomes a matrix of dimensionality 4 times 2. And that means again that my output value from the hidden layer, so A1 and A2, is also going to be a matrix of dimensionality 4 times 2. And then my weight matrix, or the vector WT, W for the final layer, which is W1 and W2 here, that is a vector of length 2 here. This is a quantity which I would multiply with A12. So A12 has dimensionality 4 times 2, and I'm multiplying with a vector which has dimensionality 2 times 1. So I would say that this one has dimensionality 1 times 2, so which means that W has dimensionality 2 times 1. So when I multiply this A with W, that has dimensionality 4 times 1. And that's what I want to compare with, because my final target value, which is this one, is a vector of dimensionality, or a matrix of dimensionality 4 times 1. So this is a way to just get a kind of feeling of how you should set up a neural network. And then clearly the next step, when we have performed this feed-forward pass, is actually to set up the final output and compare that one with the results, which we would have for the output, the target values. So what I'm going to do now, before we take a break, I'm going to switch back to the Jupyter Notebook, and we're going to look at how we can now build a neural network ourselves. So let's just swing back to the Jupyter Notebook for this specific week. But before we do that, I wanted to just say a little bit about the material which you will find. So if we now look at the upper right corner here, so you have a link to my set of lectures. So this contains it's a more complete set of lectures. And this is based on a course which I've been teaching at the University of Warsaw for years. So if we look at this, if we click on this link here, you will find an explicit example on how we build up the neural network for these XOR gates. So let's take a closer look. So when we click on this link, what we are going to get then is, if you look at the right, at the left corner here, you will find the content. If you scroll down, there is an exercise set for week 43 and 44. And in this specific case, we are actually calculating or setting up a neural network code for the OR gate or the XOR gate. And in this specific case, we are setting up a batch of data. So as I said, we are picking out the 4 possible cases which we can have. But we could have, if you wanted to, just train on one single input. So just keep in mind now that our design matrix contains now a batch of observations. And we have different output vectors, which are given by 0, 1, 1 if we have an XOR gate, or 1, 0, 1, 1, 1 for the OR gate, or if you want to train the AND gate. Now, what I've done here is to study the dimensionalities. So we have the hidden layer here, And now I'm actually just giving you values which are going to give us the correct prediction. So you could think of this W as being the result of a training operation. And you will see now that when I set this up, I have a W and I multiply X with W, and that gives me a new 4x2 matrix. I add the biases from the hidden layer, and then I have the input to the activation function. And in this specific case, I use the ReLO function, which is just the max value between each element here and 0. And you see now that the max value is obviously here 0. Minus 1 and 0 gives 0. 1 and 0 gives 1. 0 and 0 is 0, obviously. So this is just an activation function, which is extremely simple, which is these rectified linear units. And then I have the biases for the output, no, the weights for the output layer. And when I multiply this output from the hidden layer with the weights for the output layer, then I have my output, which becomes now a 4 times 1 vector. And this is since I now have assumed that these are the values for my training, I have now the optimal parameters, obviously. And the biases for the output layer just set to 0. So after the break, we are going to see how we can set up the training of this network. And the first part we are going to do then is to look at the feed-forward part with just one hidden layer. And then when we are done with that, we are going to go back to the to an example with some more realistic data, like the NNIS data, which is a set of handwritten numbers. We are going to look at regression cases, etc., etc. But I wanted to have you with me with some of these basic steps. So when we've gone through the basic steps and have built our own code, then we are going to look more next week at some of the mathematics in connection with automatic differentiation, but also what may go wrong with the training of neural network, like vanishing gradients, exploding gradients, and other technicalities which are needed in order to understand how we define a neural network and how it actually works. So we're going to take a small break, and welcome back, everybody. Now, what we are going to do explicitly now is to set up the code for running a neural network. And it's convenient when you want to set up your own code to actually go through this simple XOR example, or gate example, or AND gate if you prefer that. And in these cases, what you would do then is to train the data for these weights. So you can think of what you see in this calculation here as weights which have been trained to produce a correct result. Now, in this particular case, we're actually plugging in a batch of input values. You could have trained this on only one in case you want to do that, or you could simply duplicate, triplicate, etc. This batch of entries. And this specific batch here gives you 4 output values, which then classify the different gates. And now we know that when you're training many of these machine learning algorithms, we know that these algorithms are data greedy. So what we could simply do then is to produce new batches of results. So we could have a batch with 8, 12, 16, etc., etc. So we could even have 1,000 replicas of these. So that means you would have 4,000 entries and then train a neural network. And what we will see when we do things like that is that the network is getting better and better in setting up the final results. But for each entry, so we have one input node for X1 and one input node for X2, then we have 2 weights. Now, if you think of what we are doing here, there is a parallel to what we did when we set up linear regression. So let me quickly try to do that, because this may, in the beginning, may confuse people a little bit, because we have a batch of input values. And we have only 4 weights for which connect with the 2 hidden nodes in the hidden layer. So let's just quickly remind ourselves what we did when we trained a linear regression model. So when we trained a linear regression model, what we actually did then was to have a batch of values. So we had some y1. So let me quickly set up this. So this is a comparison with linear regression. So what we had was a batch of output values, or just a set of data, of input data and output data. So what we had was a y0, y1, y2, down to y of n minus 1. And for each of them, I had the same set of parameters. I had a beta 0, I have a beta 1 times x0, a beta 2 times x0 squared, and this went up to the final value, which we had p1 of x0 to the power of p1. And then we would repeat the same here, beta 0 plus beta 1, x1, etc. And then we would have a beta 0 plus beta 1 of x2, and just setting up like this. And that means that we could now rewrite this value y, which was now the parameter which approximated the function we want to reproduce. And we could rewrite that in terms of a matrix X times a vector beta. Now, keep in mind now that these betas, they are the same for all the points. So we are training a model on a batch of data given by x0, x1s, x2s, etc. And then we have the same parameters. Now, when we go back to the neural network case, sorry for that, what we are doing now is actually to train the input data, but with the same set of weights for all the input data. So we have a batch of data here. So just keep that in mind, because this may at the beginning may be a little bit confusing when you're setting up our own code. So when we are setting up the network here, this is the simplest possible system which we can set up. So we have the sigmoid function, which we are using as an activation function in both the hidden layer and in the output layer. And you see now that the feed forward pass contains now a matrix multiplication of x multiplied with the hidden weights plus the hidden bias. So this z value, which you see here, can be both. It can be a vector or it can be a matrix. And then my output is simply given by this input to the sigmoid function. So this is the output from the hidden layer. And then when I look at the output from the output layer, that is simply a matrix multiplication with this quantity here times the output weights plus the output bias, as we set up before. And then I'm now calculating the probabilities for the sigmoid. So since I'm doing a classification problem, I'm using the sigmoid function here. And I'm going to have a test which says that if this is less than 0.5, then my output is 0. If it's larger or equal to 0.5, my output is going to be 1. And you can see here, I'm setting up my X design matrix, and I'm setting up the outputs. I have the number of features, which is given by the shape of the design matrix, the number of inputs, the number of features. I specify number of hidden neurons to be 2. I've specified number of features. This is actually not necessary. And I have only one output. So this is going to define my output nodes. And here I'm setting up the hidden weights. So this is the initialization. I'm setting up the hidden biases by just putting it equal to 0.1 for both hidden nodes. And then I'm doing the same for the output weights and the output bias. And this is my feed-forward stage. And that's the output which it produces. So what I could say now, with these weights and biases, which I have initialized randomly, my network produces now, instead of, since now, if I would like to compare that with an OR gate, it should have produced 0, 1, 1, 1. So what I can say now is that if this output from the sigmoid function is larger or equal to 0.5, it should spit out 1. So my output here, if I convert these ones into integers, either 0 and 1, it would all be ones. So this is my feed-forward pass. Now, the feed-forward pass needs to be accompanied by a backpropagation pass. Now, if you then go into the notes here, you will find an example with the scikit-learn. And if you run it with scikit-learn with different learning rates and hyperparameters lambda, you would find something like this, that there is only one region here. This is a hyperparameter, a learning rate, which is given to 10, equal 10 to the minus 2. It starts at 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1 here. And then I have a value of the hyperparameter, which is 10 to the minus 3 and 10 to the minus 4. In those cases, I get a perfect fit. Now, if you scroll down along these lines here, there is an example of how you can build your own object-oriented code. But we are going now to step ourselves through these elements. So here you could see a full code, which also contains an answer to the exercises on writing a code for doing gradient descent methods. So this contains things like the momentum, ADA-grad, root mean square propagation, and the ADA method. So you could feel free to take a look at this, and this is something you will find if you scroll down along the left column of my collection of Jupyter notebooks for this course and into a Jupyter book here. But now I just want to go into the explicit slides, which we have for this week and which we also discussed last week. So in the beginning, you will find just the basic introduction, which we went through last week. So I'm going to skip that. And what we are going to go now is, let me just reduce the fonts a little bit. So we are going now to look at the setup of our first code. And we have the equations for the backpropagation algorithm. But now we need to set up the code here. And let's now just do that. And we are going to look at first a classification problem. So we are going to set up now a code which is going to allow us to classify this MNIST data set. This MNIST data set is a famous one which you will encounter in basically all machine learning literature, and it contains handwritten numbers from 0 to 9. So you have 10 categories or 10 classes. So that means that our output now is not a binary output, but it's actually going to be an output which is going to contain 10 cases or 10 classes. So that means that we are going to modify the standard sigmoid function for the output, which now is tailored to a binary case, as we've been discussing before. And we're going to replace that one with the so-called softmax probability. So that means that at the output layer, we are going to need a slightly different activation function, which now depends on a different set of data, which in this specific case is going to be given by 10 handwritten numbers from 0 to 9. So the cost function is the same as we have been discussing before. So it's going to be given by the cross entropy, which is the one we discussed in logistic regression. And this is a function which we are going to optimize, and that has explicit expression for the derivatives. This is the activation function for the output layer, which now is given by the softmax function. And for those of you who remember Planck's distribution in order to explain black body radiation, you will actually see clear similarities here. So what I wanted to set up now, if you just scroll down a little bit, after we've gone through, these are just derivatives which you will need to plug in. So when we are developing a code here, we need to collect and pre-process data. In this particular case, we have the data set being set up for us already, and we are going to use scikit-learn's background codes for setting up and pre-processing the data. We need to define the model and the architecture. We need to choose cost function and the optimizer. Then we train the model, we evaluate the model on test data, and then we eventually adjust hyperparameters. So the data set is originally a data set which contains 70,000 images and of 28 times 28 pixels, and with not more than one color channel. The one which we are going to look at now is a set which has been trimmed down, so the images are not of very high quality, and it's been trimmed down to less than 2,000 images, and it has 8 times 8 pixels. That means that the design matrix now, if we look at a batch of data, is going to have a dimensionality of 1797 times the number of features, which are 64, because we have 8 times 8 pixels. So this is our design matrix. And this is a little bit different from what we discussed in terms of the OR gate. So if we do this, then what we would have is the first part of the code where we now simply are setting up the images. And in this specific case, you can see now the quality of the images. So the design matrix is going to contain 1797 inputs. We could have limited ourselves to one image and just train a network on that, but that would not give us enough training data. And then we have 64 features. So this is the input matrix or the design matrix. And you see that the numbers here, really, if I look at some of these numbers, like these 2 7 numbers, it's not that easy to see that this is a 7. So when we are setting up the data now, we are going to do as before, and we are going to split into 80% test and 80% training and 20% for testing. And in this case, we just use scikit's functionality in terms of the train test split function, which you have seen before. So let's run that one as well. And that simply tells us that we are going to train on 1,437 images, and then we're going to test on 360. Now, when we then define the model and architecture, we are going to have a single layer, hidden layer. So this is normally called a multi-layer perceptron model. And we are going to have one hidden layer, one input layer, and one output layer. And we are going now to simply use the sigmoid function for the hidden layer, and then we're going to have the softmax function for the output layer. So we need to specify the input. So we have each input has 64 pixels. So that means we have 64 nodes or neurons. The hidden layer, we are going just to set 50 neurons, and that means that we have 64 times 50. So that means 3,200 weights to the hidden layer. And you see that the dimensionalities of these systems, they actually grow quickly. And if we have more hidden nodes, and if we have more input nodes, so if we have an image of higher resolution, this is clearly going to be give us a weight matrix, which is going to be much larger. You could now think of, instead of having 28 times 8 pixels, you could have 100 times 100. Then 64 would be replaced by 10,000. And that means that if you multiply 10,000 with 50 hidden nodes, then you end up with 500,000 weights to be trained. So this clearly shows you how quickly this kind of affine transformations, which we're going to perform, matrix and matrix vector multiplications, can quickly grow in size. So the inputs to the activation functions, either the softmax for the output layer or the sigmoid for the hidden layers, is simply going to be given by this Z here, which now has the unknown weights multiplied with the inputs from the previous layers, and then plus the biases. And then if we now look at the output layer, so the output layer has a connection with 50 nodes from the hidden layer, and then we have 10 output nodes. So remember now that we are not dealing with a binary problem. So a binary problem would just give one output, either 1 or 0. But then when we now have 10 images, we need to have 10 nodes. So that means that we have 500 weights. So we have 3,000 plus 500. And if we add the biases in total, we will have 3,000 plus 500, 3,700, plus 50 nodes in the hidden layer, which gives 50 biases. So that's 3,750. And then we have 10 nodes here, which gives in total 3,760 parameters to be trained. This is, in general, a very small case, but I'm simply setting up this case because this is something which we can easily run during a lecture without having to wait too much. If we increase the dimensionality, this is going to take much more time. So let's try to train this. And now I'm setting up the, I'm building my hidden nodes, and I'm building up my output nodes. I'm initializing the weights and the biases. So I'm setting up the number of features, the categories are 10. I have 50 hidden neurons, and you can see now that the dimensionalities are just plugged in here. This is the way I'm now setting up my network, and I'm initializing the weights and the biases. I have a feed-forward pass, as we discussed before the break, and right at the beginning of this lecture. And then we are performing the matrix vector multiplications. So when I perform these multiplications, I have a number of inputs times the number of hidden layers. I add the biases, I produce the output, and then this is fed to the output layer where I have the outputs from the output layer multiplied with the weights, plus the biases in the output layer. And this is fed into the softmax function. And this is the function which you now can see here. So here it actually sets up the results from the output from the hidden layer. And this is the output from the output layer, where I now am implementing the softmax function. And if I do that, you can see now that my prediction for one of the inputs, so I have the image 0, which is actually given by number 8. No, sorry, this is my prediction. And then it's actually a number 6, which is the correct label here. Now, there are some technicalities here which I just want to skip. And what we need next is to train and implement the backpropagation. So in this example, which you will see here, the first case is just a plain gradient descent. There is no stochastic gradient descent. That means that I'm setting up the full gradient and with all the weights and biases. So I have 3,700 weights and 60 biases to train. And then I'm simply now, if we scroll down here, so let's just look at the way we would perform our first pass here. So if we now look at the feed-forward pass, this is the same as before. And this returns the probabilities, the outputs from the hidden layers and the outputs from the output layer. Now, the backpropagation part, as you can see here, calls the feed-forward pass. If we go back to the beginning here, we have now initialized the weights and the biases for our first iteration. So what I'm doing here now is to backpropagate by calling the feed-forward pass. The feed-forward pass returns the output from the hidden layer and the outputs from the output layer. I'm calculating my delta function, which I call error here. And this simplifies to just the final probabilities minus the target value y. And then I can calculate this hidden error by using the formula which we set up in the beginning of the lecture. And then I calculate the gradients for the output layer by using the expressions we have discussed. And then I can set up the gradients for the hidden layer. So this function here returns the gradients, and it returns all the other parameters which are needed. So you can see now that it returns the output weights gradients, the output bias gradient, the hidden weights gradient, and the hidden bias gradient. And now take a look at what we have here. So this is my basic training for one value of the learning rate eta and one value for the hyperparameter lambda. This is not necessarily going to give us a good result, okay? So what it returns here are the gradients. And I call the backpropagation, which also calls the feed-forward part. Then since I have a regularization term, I have the derivatives of the regularization terms, which I need to add. And this is my standard gradient descent algorithm. So in this specific case, there is no stochastic gradient descent, nothing fancy. What you see here is just a plain gradient descent, nothing more than that. As simple as possible. And this obviously is something which we need to change by adding various ways of doing stochastic gradient descent. We can change the learning rate, which you see here, eta, by using methods like ADAM or root mean square propagation or ADAGRAD or other methods. But what you also see here is that we repeat this 1,000 times. This plays the same role as we discussed earlier with gradient methods, where we simply run through a number of iterations. And this could be 100 or 1,000 till the gradients were 0. Now, what we don't want here in the training is that the gradients actually vanish. However, a typical test we would plug in here would be on the cost function itself to see that those gradients are disappearing. Because at the end, it's the derivative of the cost function which we want to drive to 0. But the gradients for the intermediate stages, like with different hidden layers, they do not necessarily need to be 0, because if they are 0, the training would stop. So you see now that each iteration contains a call to the back propagation, which then includes a feed forward stage. So we are going to go back and forth here. We initialize the weights and the biases. We perform a feed forward pass. We get the outputs for the different layers, output layers and hidden layers. And then when we have that, we calculate the gradients, and then we back propagate and train the various gradients. When that is done, then we have our first prediction. So if you look at this prediction here, the old prediction was 0.14. And when I train my network, this is not so impressive. So this accuracy, which I'm setting up, just counts the number of data which I have classified correctly, divided by the total number of data. So ideally, this should be 1. But in my case here, this is 0.09. So what I'm going to do now is to repeat these calculations. And keep in mind that in this code, which you see now, there is just an implementation of a plain gradient descent. And the calculations are run for just one learning rate and one hyperparameter. So we don't know which learning rates and hyperparameters give us the best results. So that means that we have to repeat this for many, many more hyperparameters. So we are going typically to run with eta from spanning from 10 to the minus 6 to 10 to the minus 1. And then we can also have different regularization parameters. So we are going to make a grid search among the hyperparameters and the learning rates and see which one gives us the best fit. So there's a full object-oriented setup here. You can just take a look at it. And this is the way we evaluate the quality of the training, by simply looking at the test data, and then we run over the total number of data and find which have been classified correctly and divide by the total number of data. So the ideal score is 1, by obvious reasons here. So now I'm introducing stochastic gradient descent. I'm just setting up, without having tested that, the number of epochs, the batch sizes, and this is the first part. And then I'm going to adjust the hyperparameters. So I have a set of hyperparameters which run from these values. And now I train my neural network. And then I apply the trained neural network with all the weights and the biases I have trained. And I perform, if you now look at the number of iterations which I'm running through here, the back propagation piece is going to be run 1,000 times, as we discussed earlier. And so this is a pretty brute force way of performing the training itself. And when I do that, you can see now that when I improve my perform my stochastic gradient descent, this gives us actually a better score. And now I will simply run this for all the hyperparameters which I'm setting up here. And you can see typically the type of scores which you get when you have different learning rates and different hyperparameters lambda. Now, this takes some time. On my laptop, it's not the fastest implementation. And typically you would run, if you wish to, you can use Google's Colab, and because that could give you access to GPUs and CPUs. My laptop, it's a little bit old-fashioned laptop, so it's not the best one. And you can now see that when you're running here, I've now run up to a learning rate of 10 to the minus 1. What I'm going to do next is actually to visualize the data by using this software package, which is called Seaborn, which gives us a heat map. And that's going to give me a heat map as a function of the learning rate and the hyperparameter lambda. And that gives a better way to visualize the data. So you can see this is almost done now. So we have when I have a learning rate of 10, that is the result, which is going to give me, I think it's almost done now. And you can see that when my lambda value is 10 and I have a learning rate which is 1, then I'm getting into values which are pretty poor on the accuracy score, which is also expected because the learning rate of 10 is actually not the smartest learning rate which we could use. And we're also entering into problems with vanishing gradients. So I have either an overflow or vanishing or exploding gradients. So there is an overflow in the calculation of the exponential here because I have too large values. And you can see that the runtime warning here is an overflow. And this is a kind of warning that the input to the exponential function is getting too large. And this is going to give us something which is called exploding gradients. And that will give us a serious problems in the training here. But in essence, this should now be done. And so this is the final one. So we can visualize the results. And when we visualize it here, you would see something like this for the training results. So let me just see if I can make this a little bit larger. So this learning rate here is 10 to the minus 5. And then when I go down here to 10 to the, so this will be 10 to the minus 4, 10 to the minus 3. So this is on the training data. And you see now that on the training, when I have a learning rate of 10 to the minus, between 10 to the minus 2 and 10 to the minus 3, so this is 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, and 10 to the minus 2. Then I actually have a perfect training. So my training on the 1400 points gives us an accuracy of 1. When I scroll down here, if I do the same, you will see that the hyperparameter lambda, which starts from 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, and 10 to the minus 1 here, gives us a result which is also perfect. If I now look at my test data, so these are the data which were not included, you will see that I end up with an accuracy which is 96%. So it's not that bad with this simple neural network which I put up. So this can obviously be improved now by running more iterations, having a better method. So I was not using ADA-grad. I was not using root mean square propagation. I had a very simple way of updating the learning rate. And if I now use scikit-learn, so scikit-learn, I can now define the type of activation functions I want to use. By default, the scikit-learn uses Adam to update the learning rate. So in principle, that should give me better results than those which I have had till now. So if I do that, you will find a similar set of runs here. We just let it run through here, and then we're going to perform a similar plot. You will also find warnings of the type like this. So the stochastic optimizer has a set of maximum iterations, which are set by default. And that may mean that it hasn't reached the convergence criteria. And this is a kind of warning which you're getting here. So in principle, I should actually rerun this by increasing the number of iterations or adjusting the convergence criteria. So these are things which you can easily look up in the scikit-learn manual here. And then we can just let this run through here for different learning rates, and then just continue till we have the final value. And you can see now it's just gone through everything, and then we can visualize it in the same way as we did with our own data before. And in this case, you will see that it has a larger region where I have basically a perfect training. So Adam, as an optimization algorithm for the learning rate, does a much better job than my simple stochastic gradient descent without momentum and without any fancy way of updating the learning rate. So I'm just keeping a constant learning rate. And you see this is actually doing a much better job here. And then you have a much larger range where the training is almost perfect. And you can see now that you have a accuracy on the test data, which is 99%. So as far as I remember, the human accuracy here is 98%. So my training here for this reduced data set, where you see that some of the numbers are blurred, is actually better than what humans do. And for a large range on the test data, so these are data sets which were not included in the training, the machine learning algorithm based on the neural network and one hidden layer only, we have only one hidden layer, is actually doing a very good job. So this is better than what humans do, which typically are around 97, 98% on this data set. So any questions so far? So implementing your own neural network is actually not that difficult. And if you go into those notes which we discussed earlier, where we scroll down and look at the exercises from this other course for week 43 and 44, then you will find a complete code. If we now scroll down here, and this complete code contains all these elements. So this is an object-oriented code. It contains all these different methods, and you can use this if you want to, or you can use scikit-learn, or as we will see pretty soon, you can use TensorFlow or PyTorch if you're more familiar with PyTorch. So we are going to look at the TensorFlow, but let me just quickly tell you what you find here. You will find examples of cost functions. You can obviously add more cost functions. So this is basically a code which does the same as the scikit-learn code. And then it includes the, takes the derivatives by using autograd. It looks at different activation functions. So there is a sigmoid, just the identity. If you're dealing with a regression case for the output layer, there is a softmax, there is a ReLO, there's a leaky ReLO, and then there are expressions for the derivatives. And at the end, there is a code which does the, as you can see here, the feed forward pass. And there is a final one which does the back propagation part. So these are the different ways of setting up the network. And then you have the back propagation part. And at the end, what you will find then is just a way to set up the neural network. And here is a data set which you can use and train on that data set for a linear regression case. And there are also examples on how you can train. So if you just scroll down here, you can also train on a logistic regression case. So where you would have a binary output. So this is unnecessary. I should actually have put an option here where I don't print these outputs. This is actually a long set of outputs. So let's just scroll down. There's an example of how you would do that on breast cancer data and how you would then call the logistic regression case, which means you just do a binary output on this specific data set, the Wisconsin data set. So let's go back to the Jupyter notebook here. So what we said is that when we use a better type of or better form of optimization for the learning rate, then we are getting close to 100% accuracy, even with just one hidden layer. So let's just scroll down a little bit and take a look at how to include TensorFlow. So there are two very popular libraries for setting up neural networks and deep learning algorithms. And when we come to convolutional neural networks, we are going to use, for instance, TensorFlow. If you're interested, I can give you references to how to use PyTorch for the same system. So TensorFlow is actually the library, the machine learning library, which was released by Google in 2015, the end of the year. And then Facebook also released its own AI library, which is called PyTorch. And that was released in the beginning of 2016. So some people prefer to use PyTorch because they feel it's closer to the way you would program basic Python. Now, TensorFlow provides an API, which is a high-level API, which is called Keras. And Keras is something which makes it pretty easy to set up a neural network. So for us, and the specific things we will do in project 2, depending on whether you want to do standard neural networks or convolutional neural networks, using Keras as an interface to TensorFlow is something which is going to make your life much, much easier. So the way you would then rephrase this problem which we have here is first to import the data, obviously. But now what you would do is to, after you have imported data, so this is the same data set which we did before. So we would train and test and split the data and train and test as before. But then we are going to include different layers from Keras. So there's an input layer. And then we are going to have a sequential set of layers, of hidden layers. These are going to be dense. So that's just a specific way to define that we have dense layers. We are going to include different optimizers. This could be ADA-grad, it could be root mean square propagation, ADAM, or any of the other ones. We need to define the type of regularizations which we want to do, or shrinkage or hyperparameter terms. And then we also need to specify, like when we're doing the cross entropy, what kind of categories and how many of these we have. So the first part here is just to import these different features from Keras. And you would simply do that by tensorflow.keras layers. And then when we are now going to train the network, you can now see that we are going to set up 100 epochs, 100 batches. That's the batch size. I'm going to have two new hidden layers, one with 100 nodes and another one with 50. And then I'm going to have 10 categories. I'm going to have the same number of eta values and the same number of lambda values, which we had before. So eta is the learning rate. And when I'm setting up the network now, I'm simply going to have a sequential model. So that means it goes from input layers through hidden layers to the output layer. I define a dense layer here now with activation function sigmoid. I have a regularization term, which is just an L2. I do the same here. And then I have my final layer, which is the output layer, which now has the softmax function as my output. I define the optimizer, which is now given by the standard stochastic gradient descent, just a plain stochastic gradient descent, no Adam, no ADA-grad, etc. And then I define my cost function or loss function to be the cross entropy. And then the metrics which I want to specify is just the accuracy as before. So this would be my the way I would set up my network. And here I would simply run and train. Now having two hidden layers here is going to take a little bit more time. And the results are not going to be much better than we get with just one hidden layer. So that clearly tells us that the setup of a neural network is something which depends delicately on the number of parameters we set up. So the model is defined by the architecture, the number of hidden layers, the number of nodes we had. So in the previous case, we had just one hidden layer and 50 hidden nodes. Now we're just ramping this up to 150. We are using the same type of activation functions. There is no change here. We are using just a plain stochastic gradient descent instead of Adam, so that can change a little bit. So in here, if you want to, you can just replace this with Adam. So I will leave this to you to just try and run it and see what you get, and compare that with what you got with just a simpler architecture where you had one hidden layer with 50 nodes, but else the remaining parts are the same. Activation functions are the same. The stochastic gradient method is basically the same, except that we, by default, scikit-learn uses Adam. And the only thing which differs then is actually the size of the number of hidden layers and the number of neurons which we have. So this is going to conclude the lecture today. And there are some more examples on how to use the breast cancer data. And then next week, we are going to look at how we can fine-tune neural network parameters. We are going to look a little bit more into the mathematics of neural networks in connection with automatic differentiation and the backpropagation algorithm. And then the next topic, which we will dive into next week, is how to use these codes which we have developed to solve differential equations. And that's a pretty hot topic, and it's a very interesting topic. And that's something which we will spend some time next week as an application of neural networks. And these applications which are often of quite some interest to us doing natural science. After that, we are going to study convolutional neural networks and the recognition of images and classification of images. And finally, we will end the semester with a discussion of recurrent neural networks. So we will probably have the last lectures around December the 18th, roughly. These lectures will all be recorded. So in case you cannot attend them, you can always look them up. And finally, we may have 1 or 2 sessions in January where we discuss actually the solution of the projects and work on the projects. Okay, so this is going to end today's lecture.